Good afternoon, everyone, and welcome officially to our first ever University of California Observatories Living Room Lectures. It's wonderful to have so many of you here with us. Obviously, we are desperately missing you and the really great energy that you bring to Lick Observatory throughout the summer during our typical summer series, but we're just delighted to be able to connect with you in this new way. And know that for so many of you who aren't able to travel up to Lick Observatory during the summer, that this is your first opportunity to do an event with us. So are just really excited to be speaking with you today. We are just now getting really started with our virtual event series. Those of you who are friends of Lick Observatory may have participated a few weeks ago in our first ever FOLO family dinner with Alex Filippenko up at UC Berkeley. This is our first living room lecture, and then starting next Monday at 4 p.m. on Instagram Live, we will have our first Ask an Astronomer. For those of you who haven't learned very much about the Ask an Astronomer series, you'll have the opportunity through all of our social media platforms to submit questions to our first astronomer, which will be Dr. Matthew Chatrone, our Deputy Director of the University of California Observatories. And then he will be selecting from those questions and answering them throughout his time on Instagram Live. If you have any questions about how to connect to that event and that platform, you can reach out to us through the emails that we're sending and through our social media, UCO and Lick Observatory social media. First today, I'm delighted to introduce my boss, the director of the University of California Observatories. She's the reason that I wanted to come to work with the University of California Observatory. Not only has she just done incredible work and changing the way that we've been able to use ground-based telescopes to observe space. She does so in such a humble manner and is really an inspiration to all of those that have the opportunity to work with her. I hope that you find her to be just as inspiring, as she explains that not only was she a pioneer in developing this work, but the University of California and Lick Observatories in particular were the first to use this adaptive optics technology that we now use on ground-based telescopes across the world. Claire?
Let me share my screen if I can. There. Can you see that? Yes, no? I can't, now I can't see you, so you have to tell me.
Yes, we can see that, Claire.
Okay. If it flakes out at some point, just say so. So I'm going to talk about observing giant galaxy collisions with a relatively new technology called adaptive optics. And you'll see what I mean when I say giant galaxy collisions. In fact, this shouldn't keep you up at night, but our Milky Way galaxy is going to collide with the nearest big galaxy, the Andromeda galaxy, in about 1 billion years. So don't hold your breath, but we are going to be in one of these collisions that I'm showing you today, eventually. So these are the topics I'll talk about. Turbulence in the Earth's atmosphere, and the technology called adaptive optics, and laser guide stars. And I'll explain what those are. And then using adaptive optics to study galaxy mergers, galaxy collisions in nearby galaxies that have a lot of gas lying around. And I want to jump from there to what can we say about which galaxies supermassive black holes will eventually merge. So we now know that most reasonable sized galaxies have very large black holes in their core, 1 billion or 100 million times the mass of the sun. So what can we say about whether those are going to merge? And then I'll summarize. So what is adaptive optics? So here's a star And here's these red wiggles are supposed to be turbulence in the air above the telescope. And here's the telescope. And when you try and bring that star to a focus, you know, stars are so far away that they should be points of light. But instead, they're fuzzy blobs. That's a technical term, fuzzy blob. And the reason is that the turbulence has messed up these light rays coming from the star, and then they can't be focused very well. So, you know, turbulence is why stars twinkle. Since I try to compensate for the turbulence and take away its effects, sometimes my husband jokes at dinner parties that my wife is taking away the twinkle from the stars, but now we don't have dinner parties. That's too bad. But more important for astronomy than twinkling is that it spreads out the light and makes it into a much larger, not even very circular point of light rather than a tiny little one. This is actually very drastic. We have now the biggest telescopes on the ground. Optical infrared telescopes are 8 or 10 meters across. And these giant telescopes have no better spatial resolution than a little 8-inch or 20-centimeter telescope that some member of your family might have put up in his backyard or her backyard and asked you to look through. The first one I looked through was at summer camp, but when I think about it, that little telescope that I looked through at summer camp had no better ability to pick out details on Jupiter, say, or anything else than the meter that no better than that little backyard telescope. And that's so serious that we actually felt like we had to do something about it. So here's an illustration of what happens. These are all images of the same star at Lick with a little 1-meter telescope, but that's big enough to have this effect. On the left is a long exposure image of a star. The good news is it's pretty round, looks sort of star-like. The bad news is it's much bigger than it should be. So on the right, if you use this technology that I'll tell you about in a few slides called adaptive optics, this is the size that that star should be. This is the size that the turbulence in the atmosphere makes it. If instead of taking a long time exposure, you take many short snapshots, you get a bunch of images like the one in the middle. They're changing with time because the turbulence changes with time. And they're made up of these little speckles. And coincidentally, each adaptive optics image that you can do is the size of one of those speckles. But if you keep adding them up in random places over long periods of time, they smear out into this great big, almost round thing. So adaptive optics, fondly known as AO, is a technique for correcting optical distortions like this to dramatically improve image quality. And this is my one equation in the talk. So if you have adaptive optics, you can resolve an object in the sky of angular size, delta theta. And delta theta is given by the wavelength of the light divided by the telescope diameter. So a small diameter telescope, a little 8-inch telescope, will only be able to see relatively large objects that make large angles on the sky. But a 10-meter telescope, where diameter is much bigger, this fraction is smaller, and therefore you can see much smaller details. And adaptive optics is good for a lot of other things as well, but I'm not going to have time to go into them here. So how does it do this? Well, this is sort of the cartoon approximation here. I have to try and move this zoom thing. So here's your favorite galaxy. That's what you're really interested in. This bright star is an ordinary bright star. It's kind of boring, but you want to use its light to tell you how to correct your telescope to see a very clear image of the galaxy. So as we saw before, the light goes through the turbulence in the atmosphere. So does the light from the galaxy if they're very close together. And you will use the light from this bright star to calculate on a computer what the turbulence actually is. And it uses that to actually change the shape of a special mirror called a deformable mirror. that's constantly changing its shape as the turbulence changes so as to fix up the image. And I owe you an apology. My son tells me that, Mom, this is such an antiquated computer, you got to find a better image. But so I'm sorry, that's what we got here. But once you fix this deformable mirror to take a shape that cancels out the turbulence, then the light from both the star and the galaxy bounces off that mirror after the telescope, usually. And the distortions are removed, and you can take an image or a spectrum and get all those clear details that you couldn't see before. So here's a little more of a schematic that shows some of the technical parts. Now the telescope is way up and to the right above the screen, but it is collecting light that's gone through the turbulent atmosphere, and so the wavefronts are distorted. They bounce off of this deformable mirror, active mirror, and the wiggles on the mirror shape are just such as to cancel out the wiggles on the incoming light and make the corrected wavefront flat. So you're looking at plane waves here. And you have a beam splitter in the main path. It sends most of the light to your high resolution camera or spectrograph, but it steals a little of the light and sends it to what's called a wavefront sensor, which measures the difference between what you tried to correct to, namely this perfect flat wavefront, and what you managed to correct through, which usually isn't perfect. And it's not perfect for a lot of reasons. The main one is that the turbulence changed between when you took the measurement of it and when you actually changed the mirror shape. So you're always trying to catch up. And your control system takes these measurements of the wavefront, converts them into signals to send to the mirror, and then you do the whole thing all over again, continuously. So this is called a closed loop feedback control system, for those of you who need a name for this. One thing to note is that the AO system fixes the image after the light has come from the telescope. These telescope mirrors are 8 and 10 meters in diameter. You can't wiggle them fast enough or finely enough to remove all these little wiggles that are on the incoming light. So you have to use a more dainty mirror to do that. So this is what happens. This is these are two images of a star. This one has no adaptive optics, great big fuzzy blob. This one has adaptive optics. It's taken a lot of the light from the outside of this big area and put it in just a few pixels in the middle. There's still a little bit of light hanging around the outside. And down below is I've taken these same two images and just made intensity going in the vertical direction. So the image on the right, where I said the yellow and white part is the most intense. Here's the most, here's the most intense part. And what you've done again is you've taken all this light from the image that didn't have any adaptive optics, and you've put it in just 2 or 3 or 4 pixels on your camera. And so of course it gets more intense because you've gathered all this energy that was spread out and put it all in one place, basically. So one of the things that this is now being used for is people have discovered planets around nearby stars. They're called extrasolar planets. And if you imagine on the left here where there's no adaptive optics and there's a planet lurking, how do you tell? Is this wiggle the planet? Is that wiggle the planet? Is that wiggle the planet? But once you've taken all the energy and put it into a much smaller region, you could clearly tell if there was a planet out here because it would stick up against the background. So that's the kind of thing that you can use these techniques for. So these are some of the first images that we took at the Keck Observatory in Hawaii of the planet Neptune. So without adaptive optics, even with a 10-meter telescope, Neptune is pretty fuzzy, hard to tell exactly what's going on. With a telescope in space that doesn't have a turbulent atmosphere, things look a lot better. You can see a lot more details. But this is only a 2.4 meter telescope. Hubble is a wonderful telescope, but it's not very big. On the other hand, if you can correct a ground-based 10-meter telescope, much bigger, with adaptive optics, you can get a much clearer image. And the reason is that Hubble is 4 times smaller than Keck, and so the images on Hubble are about 4 times fuzzier because diameter really matters in the extent to which you can see things clearly. So let's talk about that mirror that was supposed to fix everything. So this is really a cartoon approximation. Let's say this is the surface of the mirror. It used to be flat, but we did a measurement that says that the incoming wavefront that's coming in had a bump in it that looked like this. And so you cleverly make an indentation, in the mirror that's half that depth. So here's the full depth, and the mirror has an indentation half the depth. Why do you do that? Because once the light has come in and bounced off the mirror part and come out again, it's actually had to travel exactly this distance more than it would have, and therefore you end up with a flat wavefront. You've delayed part of the wavefront and let the other part catch up. So another way to say that is that the deformable mirror evens out optical path differences. So clearly, this part of the incoming wavefront has gotten ahead of the other part, and by making it travel farther, you've evened out the optical path differences. Of course, regular waves don't have square notches evened out from them, and mirrors don't make square notches. So this is a cartoon of a more realistic mirror. It's a thin sheet of glass. It's got actuators glued to the back. When you send voltage to the actuator, it gets shorter, or when you send less of a voltage to the actuator, it gets longer. And so it's doing the same thing though. You're making the part of the wavefront coming in on the left that's ahead go a farther distance, and then when it gets reflected, the back of the wavefront is caught up. That was just one kind of deformable mirror. There are many. Here's one of the bigger mirrors that's made the way I described, where you have a sheet of glass on the front, and these actuators that you can see the top of are glued to the back of the mirror. And all the rest of this stuff is wires, so you can send signals to each actuator. You can get the same number of actuators on a tiny little MEMS deformable mirror that's about the size of a postage stamp. And you make them using the methods of photolithography that people use to make your computer chips in your phone. You can also have a big deformable mirror. So we said we couldn't wiggle the main mirror of the telescope very fast or very accurately, but the light comes into the telescope, bounces off the big mirror, and goes back to a secondary mirror where then the light gets sent down to the instruments down here. And you can make this secondary an adaptive secondary. And here's a picture of one before it was fully commissioned at the University of Arizona. And each of these wires feeds one of these actuators that changes the shape of a thin sheet of glass. And of course, when it's put on the telescope, you put a coating on the glass so it's reflective. But right now we're able to look through and see all the little magnets that are on the back of it. So that's the adaptive optics part, but you need a bright star nearby to actually measure the turbulence. So if the star and the galaxy that you want to look at are sufficiently close, and even this looks a little marginal, their rays will go through the same turbulence, and when you correct the star's turbulence, you're correcting the galaxy's turbulence. But not all stars are close to your galaxy. In fact, statistically, stars that are bright enough to do a measurement on are far away from any given place in the sky. And so really only a few percent of the sky is accessible to this trick unless you can somehow make an artificial star. So that's what we do. If there's no nearby bright star, we make our own star using a laser. So here's the cartoon again. Here's your favorite galaxy. And now you can point this laser beam right at your galaxy, or right on top of your galaxy, or right next to your galaxy. And so it'll for sure go through the same turbulence that the light from the galaxy does, and then you can measure the turbulence on the way to the galaxy. So this is what it looked like when we did this first at Lick Observatory. It's a yellow laser. I'll show you why in a minute. And it's turned out to be crucial for looking at external galaxies because there aren't enough bright stars in the sky. You know, when you look up in the sky, most of the sky is black, right? And even if you look for fainter and fainter stars, there really are not very many stars that are bright enough to do this measurement. You need about a 13th magnitude star for those of you who are familiar with magnitudes. And the brightest star that we can see is 5th or 6th magnitude. So much fainter than we can see. So the next question is, how do you use a laser to make an artificial star? I glibly said we point the laser and that's the end of it, but it's not. So it turns out at a height of about 90 kilometers in the atmosphere, there's a layer of atoms that's deposited by tiny little flecks of meteorites coming in from space that burn up in the atmosphere because they get hot and they ablate and they leave their atoms behind. So there's an increased density of sodium and iron and calcium and aluminum and all sorts of stuff up there. It doesn't last for too long, but it's pretty stable, and because you're always replenishing it with more meteorites. And so if you shine a yellow laser up into this layer where there's a lot of sodium, it will make the sodium up here glow, and you can catch that glowing light coming back at you, and it's only coming from a region that's about 1 meter across, and by the time it gets down to the ground, it looks like a star. So of course it scatters light elsewhere too, but with your telescope, you just collect the light that's coming straight from the round circle that you made with your laser beam. So I wanted to backtrack a little bit and talk about the history of adaptive optics, because I think it's a fascinating interleaving between the military communities and the astronomy communities who were working on this at the same time, basically, independently at first. So this scheme of adaptive optics was first suggested by Horace Babcock at Caltech in 1953. And the technology just wasn't there to do it. You have to do measurements 500 times a second, digital measurements. He didn't have any way to do that. He didn't have any way to change the shape of a mirror that fast. But he had all the right ideas, and the technology caught up with him, essentially. In the early 70s, there were a lot of theoretical papers. Freeman Dyson, whom you may have seen on TV, and others wrote papers on what is the limitations of this technology. Louis Alvarez's group at Lawrence Berkeley Lab built the first image sharpening experiment. It was just a linear mirror, one line of actuators. So it sharpened the image in one direction, but it worked. And then the 80s, things really started to flourish. There were projects in the military and aerospace companies and the Air Force and DARPA. And a lot of the motivation there was that President Reagan had this thing called Star Wars, where he wanted to shoot down stuff that's in space. And one of the applications was to use a laser to shoot things down. And if you were going to shine a giant laser from the ground into space, you had to correct its image quality on the way up, not just on the way down. By the way, also, the Russians were firing about 1 satellite per day at that time, and we didn't know what most of them were. So another application was to take image of satellites and try and figure out what satellite that is. Is it a communication satellite? Is it some other thing? So also in the early 80s, there's a group of largely physicists then, but now including all sorts of scientists, called the Jasons, which I'm a member of, that consults for government agencies and tries to give them advice about good things to do with their technology and what not to do. We've killed many a billion-dollar program by telling people that was a dumb idea. But this was not. So laser guide stars were sort of floating around in the military, but not this kind of laser guide star that's yellow and excites the atoms in the sodium layer. And so we wrote a bunch of papers that were classified, and the Air Force did one experiment that showed that it worked under very difficult circumstances, but they were declassified in the early 90s. And today, both the Air Force and astronomy groups all around the world are are using adaptive optics and laser guide stars. So there's adaptive optics imaging on just about every ground-based 8 or 10 meter astronomy telescope today, which I find very gratifying. So in the early 90s, I got the Lawrence Livermore Lab involved. I worked there for 30 years, and it was a very good 30 years. So we had this report in '83 that said, gee, you might want to use these sodium guide stars to shoot down space junk, but we know that large astronomical objects don't move very fast, and they would be even easier to take a picture of. Satellites move across the sky very quickly, but stars don't. So the idea sat there until 1991, and finally it was declassified. And I was sitting at lunch over here in the cafeteria at Livermore with my colleague Herb Friedman, who's a laser physicist. And we both knew about this work, and we kind of looked at each other and said, well, why hasn't anybody done this? Everybody wrote papers about it, but where's the actual laser that could do this? And we figured out, well, Livermore is pretty good at building lasers, and we knew a lot about adaptive optics, so why don't we give it a try? So we built the first astronomy class, facility class sodium laser guide star, and we did it at Lick, and then took it to Keck, and that's where it's been ever since. So here are the 2 Keck telescopes in Hawaii. The laser was a joint project between Keck and Lawrence Livermore Lab. And this is what it looks like. This is the bottom of the support for the telescope mirror. Here, you can see it, there's a mirror facing upwards. And then we send the laser light up the side of the telescope and out into space. Not very much of this yellow light gets absorbed in the sodium layer and re-emitted. It's a few percent. So when my son was small, he got very upset. He said, but Mom, what happens to the light that keeps going, the 97% that keeps going? Where's it going to go? Who's it going to hit? So I basically said, don't worry about it in kinder terms. Because it spreads out so fast, it won't even be measurable by the time it gets to the nearest star. But today, every 8 and 10 meter telescope that does imaging has adaptive optics, and most have laser guide stars as well. Okay, so that's my first topic. You now know all about adaptive optics and laser guide stars and a little bit about turbulence. But now I want to use adaptive optics to study nearby galaxy mergers where the galaxies have a lot of gas lying around. And they have a name, an acronym rather. They're called ULIRGs, Ultra Luminous Infrared Galaxies. But I spared you the acronym here. And it's very hard to tell what's happening in these messy galaxy mergers. Here's a bunch of Hubble pictures of merging or colliding galaxies. These 2 galaxies in the upper left, one of them just went through the other. These are spinning next to each other and distorting each other greatly. Likewise, the third square, the galaxies are distorting each other greatly. This is the galaxy that I'm going to show you images of. And here's 2 galaxies that haven't quite merged yet, but they're pretty well tearing apart each other's spiral arms. So these are not gentle events. If you have 10 billion stars interacting with each other gravitationally, you get quite a mess. So these are nearby galaxy collisions. We know that galaxies collide far away in the universe, but I was interested in finding out exactly how they do it and to answer one other question as well. So here's the question I was interested in asking. We now know that most decent sized galaxies have giant black holes in their cores. So by giant, I mean 10 million, 100 million, a billion times the mass of the sun. That's pretty gigantic. And they're right in the middle. And we don't quite know how they formed or how they got bigger. But one possibility is they got bigger by repeated mergers with the next door black hole. So here are 2 galaxies in a computer simulation that are coming together. They get very close by so that the gravitational force of one on the other really forces all the gas to merge together, and eventually the black holes to merge, and they make a very bright quasar for a short time. It emits all sorts of X-rays and gamma rays and infrared light, ultraviolet light. And after a while, the quasar doesn't have any more matter flowing into it, so it quiets down, but you're left with vaguely spherical remnant of a galaxy, and there are spheroidal galaxies, so we think that's where they come from. And somewhere in here is a quiet black hole, and possibly it's got the sum of the two masses of the incoming black holes. So will the black holes merge? We know that they can get close to each other, but it's also possible that they could just keep going around and around each other forever. And my example of that is if you replace the Earth one night when we were all asleep by a black hole of the same mass as the Earth and put it in the same orbit as the Earth, it would just keep going round and around the sun the same way we do. So you need some sort of dissipation, some sort of torque, some sort of asymmetric gravitational force that will stop the black holes from going around and around each other forever and actually allow them to get close together. And that's what we're looking for, is what could be doing that. So here's just one example. It's called NGC 6240. This is a galaxy. It used to be 2 disk galaxies. It's got a double nucleus if you look closely at it. This is a visible light image with Hubble. It's making stars like crazy. And each of these black holes is actively accreting gas. We know that because they're emitting X-rays and radio waves as well. But it's a nice target for us because it's relatively nearby, only 300 million light years. It's very luminous. It's got this double nucleus, so we can ask whether the nuclei are going to merge. And these funny things here are what's called tidal tails. As the gravitational force of the 2 galaxies approaching each other stops being spherically symmetric, these great big tails of stars and gas get pulled out away from the galaxy itself. It also has a nice bright star nearby that we use as our adaptive optics guide star to measure the turbulence. And so it's about 35 seconds of arc away from the nucleus, and that's fine. We got good measurements from that. Nowadays, we would use the laser and just point it straight in the middle. So we want to first compare this visible light image with Hubble and zoom in on this nuclear region and see what that region looks like with Hubble's infrared camera called NICMOS. So here's this region blown up as seen in the NICMOS infrared camera on Hubble. And you can see the 2 nuclei, that one and that one. If each one of them contains a black hole, it's a little puzzling where it is, because there's a lot of different features in here and in here. If we look at it with a 4 times larger telescope, we can see a lot more. So here's structure in the north nucleus. We later showed that this is where the black hole was in the northern nucleus. There's a lot of structure in the southern nucleus and tons of dust. And so it turned out the black hole in the southern nucleus was actually up here. And we couldn't see it even in infrared light because it was obscured by dust. But if you looked at longer wavelength infrared light, you could see it. By the way, each of these things is a cluster of newly forming stars. And so, one of the questions you can ask is, do these clusters that we see of newly forming stars, do they evolve into what we now know today as something called globular clusters? The Milky Way galaxy has many globular clusters. They're just perfectly round clusters of stars, very old stars. So is this what they looked like when they were babies, essentially? So you can see with adaptive optics, larger telescopes have better spatial resolution and you can learn a lot more. So one of the next things we did, was to actually identify where the black holes were. And so this is the same data, but I've stretched the relationship between color and intensity so you only see the 2 nuclei. And the white contours are radio emission that's very characteristic of what comes from a black hole. It was obtained by Gallimore and Cooper, I think, in England using a radio array called Merlin. And sure enough, the northern one is right where we thought. The southern one, as I said, is a little farther up, and it's obscured by dust. But when we knew finally where it was, we could do an even longer wavelength infrared image and see clearly that the brightest spot of emission was right where the radio source was. Okay, so we know where they are. Because we know where they are, we were able to measure their mass. That's a different talk. You can measure the mass of a black hole by measuring the velocity of the stars that are whizzing around it. And the faster they whiz, the higher the mass is of the black hole. But we wanted to ask something else. We wanted to ask, what can we say about whether galaxies, supermassive black holes, will eventually merge? They're pretty far away here. They're like 700 parsecs away. So a parsec, I forget which this is. A parsec is 3 light years, or a light year is 3 parsecs, but something like that. So they're let's say 1,000-ish light years away from each other. So they got to get a lot closer in order to merge. How do they get closer? And so there's been a lot of beautiful computer simulation studies that shows that if you have a lot of dense gas right down there in the nucleus where the black holes are, it can help them to merge together. So you have to provide a reservoir for feeding gas into the very close regions, the central parsec, where the 2 black holes are. And if the gas can get in there from about 20 parsecs where we observe it, there's drag on the gas as the black holes try and smash their way through the gas. They're moving supersonically through the gas. They're driving shock waves into the gas, and they're slowing down and losing angular momentum, and that means that they can move closer together. And the gas disks do something else to help too. They're making stars. And so they can spew out young stars that also move in to the central regions close to the black holes. And the black holes can experience friction just from scattering off the stars, not just the gas. So we think we see mechanisms by which these black holes can eventually merge. We can't prove it. They won't merge for another 100 million years or so. But we think we can start to say what fraction of binary black holes will eventually start to merge together. And we've seen these dust disks in all 17 of the 17 objects that we had observed as of a couple of years ago. They're about 500 parsecs across. They're always there. They're vigorously forming stars. And they are capable of slowing down the black holes and making the young stars that can also slow down the black holes. So what about merging black holes? There's been a lot of wonderful news of the last several years about merging black holes. There are gravitational wave detectors called LIGO, which measures the disturbance in time and space that's caused when 2 black holes circle very fast around each other and eventually merge together. And LIGO hasn't seen the kind of giant black holes that are in these big galaxies, but they have seen lots of black holes merging that are sort of tens of times the mass of the sun. And here's what you see. What you look for is for 2 points in space to get slightly farther apart from each other and then come slightly closer together. By slightly, I mean 1 part in 10 to the 21, very slightly closer together, very slightly farther apart. It's called strain. And so these gravitational wave detectors measure very accurate distances between 2 or 3 objects. And they actually see the distance change periodically as the wave goes by. So this is the actual signal. This is what you would expect from a computer simulation. And what you can see both in the data and in the computer simulation is if you were to imagine that you're making this into a sound, so sound waves, if they're long wavelength sound waves, they're low frequency. If they're short wavelength sound waves, they're high frequency, very high pitched. So when these things are starting to spiral in, they emit low frequency waves. And as they get closer together, they go around each other faster and faster. And finally, they end up emitting very high frequency sounds or perturbations. And so if you take this signal, which is just a distortion of space, but you pretend that it's actually a sound wave, you can recreate what this would have sounded like. And so here are two different gravitational wave antennae, one in Oregon and one in Louisiana. They have to see the same thing or it's a false signal. And there's a lot of background noise. So first you'll hear background noise and then you'll hear, and the starts at low pitch and then ends at a high pitch. So this is frequency going up. This is low pitch, this is high pitch. And so this video was made first sort of at its natural frequency, and then they increased it to a higher pitch so our ears would have a better chance of identifying it. So this was so exciting when it first happened that many astronomy departments in the country, instead of people greeting each other in the hall by saying hi, they greeted each other by saying, "Rup, rup." And we even were doing that in our family. It was fun for a while. Got boring after a while, but anyway, this characteristic sound of "rup" is the change in frequency of the gravitational waves. And by the time you get to here, the two black holes have merged into one, and the pattern of this ring down tells you a lot about the mass of the remaining black hole. Now, there's another video that's trying to show you how gravitational waves distort space. So this is supposed to be a grid like a piece of graph paper, I guess, but it has two black holes going around each other, and so when they're still pretty far apart, they just make very mild distortions of this space. As you'll see, as they get closer and closer together, the distortions get bigger and bigger, and they propagate faster and faster. So here we go. I hope I can do this. So they're still pretty far apart. They're emitting gravitational waves. That lets them get closer and closer together. And pretty soon they're going to go zooming around each other, emitting great big gravitational waves. So maybe I can show that again. Let's see. Start out far apart. The amplitude of these waves isn't too high. You'll notice right at the end, the amplitude of the waves is very high as they actually merge, like right now. Okay, well, this is cool. But these black holes that were, let me go back here. These black holes that were merging were tens of times the mass of the sun. We want to be able to measure the gravitational waves from black holes merging that are 100 million or 1 billion times the mass of the sun. And that's very hard because they're very, very low frequency waves, very, very, very long wavelengths. And there's not really any way to do that using the same methods that are used by LIGO. And in the next slide at the end, I'll tell you how that can be done. So to summarize a bit, adaptive optics has allowed us to measure both the position and masses of supermassive black holes in colliding galaxies. And we characterize the conditions of these dense disks of gas and stars in the middle to understand how they can slow down the rotation of black holes and permit them eventually to merge together because they've gotten closer and closer. And the LIGO Gravitational Wave Observatory has already seen stellar mass black holes merging, or at least tens of stellar masses. And the next question is going to be, what about the much larger black holes, such as the ones that live in the nuclei of large galaxies, or even ones that are 1,000 or 100,000 times the mass of the sun. So there's this effort called the Pulsar timing array, which I'll describe in a minute. And it is our next great hope for being able to detect gravitational waves from 10 to the 8th to 10 to the 10th solar mass black holes in the next few years. And so what is a pulsar? A pulsar is a neutron star that rotates very, very regularly and emits pulses of radio waves that reach us. And so every rotation period, we get a pulse of radio waves from the pulsar. And we know exactly by timing it over tens of years, exactly what its pulse rate is. And we've even measured the slow drift in the pulse rate as they slow down a little bit by bit. So these are detected by radio telescopes, because that's how you detect radio waves. And there's an array of radio telescopes spread over the Earth. I think it's mostly the Western Hemisphere now, but it will be over the Eastern Hemisphere as well. And they are all staring at the same pulsars in space, spread out over our galaxy. The pulsars are different distances from us. And so if a giant gravitational wave goes by, it will change the positions very slowly of each of these pulsars relative to each other. And we can measure that happening by looking at how that changes the radio signal from these pulsars, because it'll get slower or faster depending on whether the pulsar is moving toward us or away from us from the gravitational waves. And so, the plan is to keep looking, and in the next few years, maybe 10 years, we're pretty giant black holes. So thank you very much. Now I can see you. No, I can't. How do I stop this? End of slideshow.
Great. Well, during most of our living room lectures, the astronomers will not be taking questions, but we're lucky that we have the director today and that she is willing to take questions. If anybody wants, you can just add that question to the chat, and we can work through those questions there.
Or you can just call out.
Yeah. Claire, do you see this question here in the chat, or would you like me to read them?
Read the chat, okay. I'm looking for the person who had asked it, but that's okay. Does sodium laser guide star stimulated emission interfere with the spectroscopy of the target object? Good question. So stars and planets and other things have sodium atoms in them. And so the implication is, if you're shining this very bright yellow laser at the thing that you're trying to measure different elements in, including sodium, doesn't that mess you up? And the answer is it doesn't, because everything's moving. So when an object is moving away from us, it's like it's a little bluer. When it's moving toward us, redder. When it's moving toward us, the light gets a little bluer. And so our sodium line is stable relative to us, whereas the sodium lines, atomic lines, in these other objects are not, because everything's moving in various directions. Unless it was moving exactly sideways, then we'd be in trouble, but that doesn't seem to happen very often. Okay, hold on. I have a phone call that I've got to get rid of. Sorry, that's our landline phone, and I never figured out how to make it quiet. Can you describe a little more about how the mirror that deforms the adaptive optics works? So maybe I can go back to one of these pictures. There are a lot of different ways that they work. There isn't any one answer, but we'll talk about the easiest one maybe. Yeah, so this is a cartoon. I have to share, I guess. Share. So you should imagine, and this is the oldest kind of mirror. This is a block of metal that doesn't move at all. And you've glued actuators to it, and they're made of PZT or PMN, and those are just ceramic-like materials where if you apply a voltage to the back, they'll get longer or shorter. And so coming out of the back of these deformable mirrors are lots of cables, which is what sends the voltage to these actuators. And the actuators on the top are glued to a very thin sheet of glass. So when this actuator gets a little longer, it pushes the glass up. When it gets a little shorter, it pulls the glass down, and then it makes these shapes. The caution is that this is greatly exaggerated. The differences in the ups and downs are very minor compared to what I've drawn here. I was just trying to illustrate things. One of my big disappointments when we first started running the adaptive optics system at Lick Observatory was I wanted to go over there to put my head looking down on the mirror and see it wiggle. And it turns out the amount that it wiggles is so small that I couldn't see it. It was devastating. But anyway, that's that kind of mirror. We can talk at more length later about the other kinds of mirrors if you want. So I should stop sharing somehow. Okay.
Does anybody make adaptive optics for amateur telescopes, like high-end reflectors or refractors?
Yeah, good question. So SBIG, the Santa Barbara Instrument Group, used to sell, I think maybe they still do, an adaptive optics system. But it's not this kind of adaptive optics. What it does is it's like a very fast tracker that will stabilize your image instead of having the image jitter around. And if the wind is blowing your telescope, you know, it'll settle down the image so it won't wiggle. I don't know of anybody who's selling real adaptive optics for amateur telescopes, and there's a good reason for that, which is that the typical scale of telescopes for which you start needing adaptive optics is pretty big. Maybe your 22-inch telescope, but you know, a little 8-inch telescope won't even benefit from adaptive optics, and that's because the wiggles and the turbulence are coherent over 8 inches. So they're not making these little itty bitty wiggles that I was trying to show you on the cartoons. And so you might do just fine with one of these things that stabilizes the image on the sky, a tracker of some sort, or just an ordinary fast tracker.
And so what you just said accounts for the reason why several times I've been at Fremont Peak and looked at, say, Jupiter through the big telescope, and I have a 5-inch Takahashi refractor, and just people come down and they look at that and they say, oh my God, this is a better view than the big telescope.
Yeah.
Which it is.
It's definitely related to that.
Yeah.
It's not, what you just said is not quite right, but that's the spirit of it.
Claire, we have some questions from Facebook as well. Brian Snar on Facebook is asking, what's the time frame for the black holes that were observed emerging in your slides earlier? And we had a similar question asking about what was the time frame of that noise?
Yeah, that's the same question, really. Okay, I'm gonna go back to my slides here. Because I hope there's a scale on it. There is not a scale on it. It's a few seconds. I don't know how many a few is. But you know, so these are black holes that are 30 or 50 times the mass of the sun, and they're whizzing around each other in a second or a fraction of a second. It's kind of amazing. There's a funny story about this. It's not funny, but anyway, there's a story about this. when they got started on LIGO, they were pretty sure that they wouldn't just be able to look at the signal and pick it up and say, ah, it's a black hole, because there's a lot of noise. You heard the noise in the beginning of that recording. And so they developed a lot of computer simulations. That's what this gray thing is here, which they call templates. And what they planned to do is, once they had collected all the data from a whole LIGO run, which was a couple months, or maybe even just from a whole night, they would run their template over it. And when they got to something that sort of looked like the template, they'd say, ah, we've got a black hole merger, because you can't pick it out with your eye. So the first black hole merger that was detected was not detected by that at all. It was a test run before the first main run. And there was, I think, a postdoc or a young astronomer in Europe who was looking at the signal as it came along, just on a monitor. You can imagine this scrolling by. And this thing scrolled by and he says, God damn it, that looks like a black hole merger. So he didn't need no darn template or anything. He just picked it right up with this computer in here. And that hasn't happened very many times, but it's fun to think that the human can sometimes do better than the computer.
We have a question about how you can even tell that a black hole merger is happening when nothing comes out of them. How do we detect black holes with radio waves if nothing can come out?
Oh, I see. So yeah, nothing can come out once it's in the black hole, but there's lots of crap lying around it. Sorry. So an accretion disk, which is feeding matter into the black hole, and the accretion disk has a magnetic field, and fast electrons in the magnetic field emit radio waves. The hot part of the disk right close to the black hole emits X-rays. You can tell that it's there. We can't. I thought you were asking how can we tell from those signals whether it's merging. I think that's much harder. And usually if black holes merge with each other, there isn't much of an electromagnetic signal that a telescope can see. But there have been a couple of mergers of neutron stars with black holes where there's matter getting strewn all over the place as the black hole tears up the neutron star. And those have been seen by some of my colleagues in a regular telescope.
He asked that if we managed to somehow put an artificial star that we created into space, could we use that instead of a laser?
Yeah, the first person who suggested something like that facetiously was to get a high altitude helicopter and shine a flashlight down. You can do it, it would be fine. The problem is that the telescopes typically observe at one place in space for half an hour, and then they move to someplace else, and then they move to someplace else. And space, because of Newton's laws, space satellites are zooming around the Earth. And the ones that don't zoom around the Earth up at geosynchronous orbit, it's going to be very hard for them to be bright enough to use as a guide star because they're so far away.
We have just hit 5 o'clock, so I wanted to thank Claire again. I know that some of you have other appointments and obligations for the dinner hour. Thank you for joining us for this first ever living room lecture, University of California Observatories. We plan to continue these throughout the summer and into the fall and winter time. This is something that we started specifically now because of COVID-19 and because we had to cancel the summer series, but something that we'd been hoping to do for a long time anyway. So we're looking forward to continuing those. We have these living room lectures, and if your favorite part is the question and answer session, we will also have Ask an Astronomer, which will just be the question and answer sessions. You can submit your questions through all of our UCO and our Lick Observatory social media platforms. And then our astronomer will be selecting questions from those every other week. Our first one is next Monday at 4 o'clock. Check your email and our social media for more information on how to join us for that. Will be our Deputy Director, Dr. Matthew Chatrone. Claire, any last words before we sign off officially here?
Oh, this is fun.
Yes. Thank you all
I
so
hope
much.
you enjoyed it as much as I did.
Yeah. Absolutely. Thank you all so much for taking time out on this Monday to join us.
Okay. Bye.